Hello students, welcome back to the second session. In the previous session, we studied about various nuclear properties such as nuclear charge, nuclear radius, nuclear mass and nuclear density. So in this session, we start with the next nuclear property, that is nuclear binding energy. So as we know, the nucleus consists of protons and neutrons, that is the total number of the nucleons, and mass of the nucleus, it is somewhat less than the sum of the masses of the constituent protons and the neutrons. So this difference in the mass, that is difference between the mass of the nucleons and the mass of the nucleus, that is called the mass defect, and it is denoted by delta M. So delta M, it is a very small difference of mass between the mass of nucleons and the mass of the nucleus. So it is equal to delta M is equal to number of protons into mass of the protons plus number of neutrons into the mass of the neutrons minus mass of the nucleus. So this term, this total term Z into Mp plus N into Mn, this is the mass of the nucleons, which is somewhat more, minus mass of the nucleus. So this small difference is called the mass defect. So the energy equivalent to the mass defect is called the binding energy. Binding energy can also be defined as the energy required to disintegrate. Disintegrate means break a nucleus into its constituent particles called the nucleons or protons and the neutrons. Binding energy, it binds all the nucleons together within the nucleus. As we know, E is equal to m into c square. But here binding energy, that is equal to delta m into c square, where delta m, it is a small difference in the mass. So from the previous slide, we have substituted the value of delta m here into c square, and from this relation we can calculate the mass of the required nucleus. That is, this is the mass of the nucleus, where nucleus is denoted by x. A is the total number of the nucleons and Z is the total number of the protons in the nucleus. So that is equal to number of protons into mass of protons plus number of neutrons into mass of the neutron minus binding energy upon c square. Now we come to binding energy per nucleon. The amount of energy required to release a nucleon from the nucleus, that is called the binding energy per nucleon, and it is denoted by binding energy divided by A. So here I write, suppose this is our nucleus having A nucleons, Z protons and N neutron, where A is equal to number of protons plus number of neutrons. But here we want to calculate the binding energy per nucleon divided by total number of the nucleons. Suppose we have the calcium nucleus having 40 total nucleons. So binding energy, if we want to calculate the binding energy per nucleon, then binding energy divided by 40, that will be the binding energy per nucleon. So this relation comes out to be equal to binding energy per nucleon, that is equal to this value. So binding energy per nucleon, basically it determines the stability of the nucleus. If the binding energy of a nucleus is less, then nucleus is less stable, whereas if the binding energy per nucleon is more, then the nucleus is more stable. That's why we say that the heavier nuclei, they are less stable as compared to the lighter nuclei. So it is an important parameter, binding energy per nucleon, it is an important parameter to determine the stability of the nucleus. Now, other useful and interesting property of binding energy, that is the neutron and the proton separation energies. The energy which must be imparted to the nucleus in order to separate a nucleon from the nucleus, or the energy liberated when a nucleon is added to the nucleus, that is called the energy of separation or the energy of addition. It is also called the separation energy. So it may be a neutron separation energy, or it denoted by Sn, or it may be a proton separation energy denoted by Sp. So neutron separation energy, it is the amount of energy that is required to remove a neutron from the nucleus. That is required to remove a neutron from the nucleus. So here Sn, that is equal to binding energy of this nucleus, that is the standard nucleus, minus binding energy of from which the neutron has been removed. Here n minus 1, that means neutron has been removed from this nucleus. When the neutron is removed, then the mass number will also decrease by 1, because total number of nucleon, that will remain the same. So this is the value of the neutron separation energy, and when we substitute the value of this binding energy for this nucleus minus binding energy for this nucleus, then some terms cancel out and we are left with this relation. And similarly, the proton separation energy, it is the amount of energy required to remove a proton from the nucleus. Fine. So this is the proton separation energy. Here the proton Z minus 1, okay, proton they have been decreased and neutron they are fixed. So A minus 1, total number of nucleons will also decrease. So our proton separation energy, it comes out to be equal to this relation. So these are the protons and the neutron separation energies, and both are positive for all the stable nuclei and are analogous to the ionization energies in the atomic physics. They tell us about the binding of the outermost or the valence nucleons. Just like the atomic ionization energy, the separation energy show evidence for the nuclear shell structure that is similar to the atomic shell structure. So we gain valuable clues to the nuclear structure from the systematic study of the nuclear binding energy. Now, this is the binding energy curve that varies from 4 to 260, and on the y-axis we have binding energy per nucleon that varies from 0 to 9. So as we see that on the left hand side here, in the mass number between 0 to 4, this point, this is the lower value of the binding energy, and this lower value of binding energy, that is for the deuteron, and its approximate value is 1.11 MeV. So as we move towards the heavier nuclei from 4 to 20 in this mass range, we have 5 different peak for different nuclei. And in the region of the small mass number range from 2 to 20, there are sharply defined maxima and minima. These are the maximas, 5 maximas, and then we have corresponding 5 minimas. So the maxima correspond to the high stability, and it occurs for even nuclei, that is helium, beryllium, carbon, oxygen and neon. These nuclei, they have even Z and even N values. That's why they are called the even nuclei. And in all the cases we have N is equal to Z, means number of neutron, they are equal to number of proton for these 5 nuclei. So this is the region of the high stability, and this region is called the region for the magic number nuclei. So these are more stable as compared to their immediate neighbors. The minima corresponding to the low stability, it occurs for lithium, boron, nitrogen and fluorine. These are called the odd nuclei which exist at the minima. So odd nuclei, so they are comparatively less stable as compared to the even nuclei. Then as we move further around at between 40 to 60, this is the maximum value of the binding energy, and maximum value of binding energy, it occurs for the most stable nuclei that we all know, iron 56, and its value is approximately 8.8 MeV per nucleon. So this is the minimum value of the binding energy for deuteron, that is 1.11 MeV. This is the maximum value of the binding energy that exists for iron 56, and its value is 8.8 MeV. And the average value of the binding energy for most of the nuclei, average value of the binding energy, that is approximately 8 MeV per nucleon, and the curve is relatively constant except for few lighter nuclei, because here for few lighter nuclei we have sharply defined maxima and the minima. Now, when we come to the right hand side here in this side, then we have very heavier nuclei. So, nuclei with A greater than 220, they are distinctly unstable. So, here is one important point to discuss, that on the left hand side we have lighter nuclei, and on the extremely right hand side we have the heavier nuclei. So heavier nuclei, they are also unstable, and the lighter nuclei, they are also unstable. So both the lighter as well as the heavier nuclei, they want to move toward the stability point, that is our this point. Okay, so lighter nuclei, they fuse together to form a heavier nuclei, and they approach towards this point. So here in this region, the process of fusion occur, fusion of two lighter nuclei to form a heavier nuclei, while on the right hand side we have the heavier nuclei. So heavier nuclei, they go through the process of the fission. They break up into the lighter nuclei, and then they move towards the stability point. So fusion and fission, these are the two important processes that are explained by this curve to explain the stability of the nuclei. So here I have written some important points that we discussed, that the minimum binding energy per nucleon is for deuteron, that is 1.1 MeV per nucleon. Then we have maximum binding energy per nucleon for iron, that is 8.8 MeV per nucleon. Then average binding energy, that is 8 MeV per nucleon. Then high stability occurs at 5 peak values, and they correspond to helium, beryllium, carbon, oxygen and neon. These are also called the even nuclei, or these are also called the magic number nuclei. And nuclei with mass number greater than 220, they are highly unstable.